In this session, I'll discuss some of the features Amazon DynamoDB customers are using to deliver an optimal experience for consumers of their own products and services. My name is Pete. I started my career as a Unix systems administrator at an early internet service company back in the days of BSDI and SunOS. I grew my experience as we made our way toward becoming a Tier 1 global network provider. I also spent some time at a company that provides cellular emergency call routing as a systems architect and manager of sysadmins and DBAs. I've architected storage area networks, run global domain name services, web applications, email, and authentication at large scale. So you get the picture. I'm very old. But age alone does not explain all of my gray hairs. Many of them are the result of countless failed power supplies, bad switch ports, dying disk drives, and the constant requirement to tweak and tune and solve for strange behaviors whenever the infrastructure was being refreshed. I went around that cycle so many times that I considered changing my name from Pete to Repeat. And I started to realize that lots of other people like me were having to solve all the same problems in their own data centers. There had to be a more efficient approach, and I was hearing great things about the AWS cloud. I started at AWS in 2016 as a technical account manager, the part of an account team focused on customer operational success. Early in my onboarding, I learned that I'd be supporting a little company called Amazon.com. Amazonians outside of AWS have an AWS account team and enterprise support. Amazon has been operating infrastructure at scale for a long time, well before the advent of AWS. And to some extent, they had adopted various foundational AWS services as building blocks to support their rapid growth. Our goal was to assist Amazon teams as they moved fully into AWS and to help them build around more of the newer AWS services with higher levels of infrastructure abstraction, to offload more of the heavy lifting and to innovate faster. I spent most of my time supporting their database modernization efforts to help them move to managed services, break free from commercially licensed database engines, and adopt a purpose-built strategy for their indexing needs. As a TAM, I ensured that Amazon teams got the help they needed from AWS support engineers. I reviewed services for peak load readiness, and I provided education around operational best practices. I came to love Redshift, Aurora, and DynamoDB. Watching Amazon teams work together to achieve their database modernization goals was an amazing experience. It took a lot of work, but I have seen the returns far outweigh the investment. As a TAM, I served as the point of AWS escalation in operations rooms for peaks like Prime Day, and over the years, I saw DynamoDB remove so much of the operational burden. AWS purpose-built databases are accelerating the rate of innovation for Amazon developers every day, and they are certainly not a unique customer in this regard. As Amazon was completing their database initiative, I thought about how I could share what I'd learned to the benefit of other AWS customers. And I decided that a solutions architect role specializing in one of the AWS purpose-built databases would be a great path. DynamoDB was my choice because I was so impressed by the difference it can make in reducing operational overhead. Serverless with zero downtime and extreme scaling elasticity. Today I'm working much more with external AWS customers to help them build new workloads on DynamoDB or migrate existing workloads as part of their broader business goals. DynamoDB specialist SAs build and deliver content to help developers and architects better understand how to use DynamoDB effectively, and we also work very closely with the engineering team to gather customer feedback, which can help prioritize feature requests. I spend a lot of my time reviewing data models with external customers and with a lot of our own AWS teams too, to optimize their designs for efficiency, performance, scalability, and data correctness. Okay, that's more than enough about me and the background that I bring to this presentation. Let's move on to the interesting stuff. The session assumes some familiarity with DynamoDB. You may know it as a database service offered by AWS since 2012. And you may think of it as a key value store, though its indexing functionality supports more complex relationships and a document interface. It might be supporting some of your applications today, chosen for its ability to deliver the highest levels of availability with consistent low latency at any scale. One request per month to millions per second. Pay as you go with minimal ops burden and data operations exposed by a RESTful API for ease of development in service-oriented architectures. Some of you might be thinking, but wait, there's more. And that is the real point of the session. I'm going to talk about the features and the tools that you see listed here and how they can be used to raise the advantages you see with DynamoDB to a new level. First up, on-demand capacity. When DynamoDB was released in 2012, it provided customers with an ability to provision the amount of read and write throughput they wanted their table to support. And this provisioned capacity mode is still available and very popular today. Based on the provisioned capacity signal, the service distributes the data across a number of storage nodes, scaling the table horizontally to be sure it can deliver that provisioned throughput in response to the application's consumption. The provision capacity can be dialed up or down as required, and the billing is according to the read and write throughput provisioned, with hourly granularity. In 2017, we introduced a feature to provide auto-scaling of this provisioned capacity, based on trends seen in CloudWatch metrics for capacity consumption. Auto-scaling helps a lot of customers to achieve better utilization of their provisioned capacity. In November 2018, we added a completely new capacity mode called On-Demand. In on-demand mode, we don't require the customer to specify a read or write throughput level at all. We build out underlying infrastructure to back the table based on direct analysis of the consumption we observe within the storage nodes. No need to observe a trend in CloudWatch metrics over time. At a fundamental level, DynamoDB tables, regardless of capacity mode, scale by partitioning and non-disruptively split partitions to double the throughput potential for your data as required. This allows the service to scale out exponentially and without ceiling. In provisioned mode, we are dependent on signal from the customer and CloudWatch metrics to drive this. But in on-demand mode, we can react much more quickly to scale faster. DynamoDB does not merge the partitions, so the future capability of your table to absorb rapid load increases is driven by your past high watermark. In provisioned mode, you can consume within that envelope only according to the level you have provisioned. In on-demand mode, we allow you to use the full capability of all the underlying partitions at any time, instantly accommodating highly variable load patterns. While auto-scaling of provisioned mode may achieve high utilization efficiency, on-demand is 100% efficient because you are paying only for the requests that you make. Let's take a look at an example of how this on-demand scaling works to cover changing loads. In this graph, we can see the throughput consumption in green, the x-axis is time, in red we see the throughput potential of the table, which is determined by the number of partitions, storage nodes across which the data is distributed. We can see that as the load grows and nears the maximum, DynamoDB recognizes that the table may require more throughput potential. Partition splitting occurs, and we now have a new maximum. The load again reaches a new peak, and DynamoDB again splits partitions to increase the potential of your table. Each round of splitting can take around a half hour, but typically much less than this. Each partition is continually analyzing the throughput it is serving and the way your traffic is distributed across the data. And it makes intelligent decisions based on this. Notice that while our load sometimes drops to zero, the potential for the table never decreases. We're not paying for any consumption or any provisioned level of throughput, but when the load returns, our on-demand table is instantly able to cover it with 100% utilization efficiency. On-demand throughput sounds quite magical, doesn't it? There is some infrastructure associated with delivering this experience, and that is built into the pricing for on-demand capacity. Currently, you can read 1 million 4 kilobyte items with strong read-after-write consistency in US East 1 for 25 cents. There is a tendency for some to compare this to the pricing of provisioned capacity and to conclude that on-demand is comparatively expensive. In making the comparison, an assumption of 100% utilization efficiency is often made for provisioned capacity, but this is rarely achievable. We offer the choice of capacity mode because load patterns vary and so do business priorities. I'm often asked how to choose a capacity mode. Before we dig in on that question, we should really distinguish between price and cost. Price is what we charge customers to use the service. Cost includes the time of your technical resources. Adjusting an auto-scaling policy and smoothing things out to get best utilization in provisioned mode takes time and should be checked and maintained periodically. Recognize that this time could potentially be spent working on things that deliver greater value to your customers. Reducing complexity in operations also minimizes risk and tends to improve availability. Some customers I've worked with have a large number of DynamoDB tables supporting a multitude of microservices, many of them being very low throughput, perhaps even development or test environments which see only sporadic activity. I encourage customers to establish a threshold for throughput spend. Maybe for you it's $500 a month. If your table would consume less than this threshold in on-demand mode, simplifying your operations is likely worth the price. Additionally, consider the life cycle of your data. Perhaps you have tables sitting around and you need to keep the data, but you aren't actively reading or writing. The minimum for provisioned capacity is one read capacity unit and one write capacity unit. You can eliminate that throughput spend by switching to on-demand. We believe that on-demand capacity is the right choice for most DynamoDB tables. Prioritize the time that you spend developing and maintaining optimal auto-scaling policies by spend. It turns out that mature workloads tend to have more predictable load patterns. On this slide, we see a few different throughput consumption patterns. At top left, we see consumption that might be one of those sporadic use dev test tables. This is a slam dunk for on-demand. At bottom, we see what is likely a significant load. It might be a mature use case, and it has a fairly predictable seasonality. This looks very familiar to me. It could easily be the diurnal pattern of traffic that a customer like Amazon.com might see in a particular market. You can see that in this case, the provisioned capacity in blue is auto-scaling very nicely indeed. It's worth spending the time to dial in a policy for such a workload. What about the consumption pattern in the middle? This is interesting because there's some load that follows a predictable pattern, along with some sporadic and irregular spikes which go well beyond the norm. These look very unpredictable and short-lived. If we cannot smooth them using queue-based load leveling, caching, or similar, on-demand capacity will likely be the most cost-effective choice. In provisioned mode, we'd likely need to maintain a minimum provisioned throughput level that can accommodate these spikes, throughput each hour or throughout each hour, every hour, and that may result in higher spend. One last note, it's easy and non-disruptive to switch between the capacity modes. We have customers who switch to provision mode to build out a new high watermark for a maximum throughput ahead of an expected event which will deliver a step function increase in traffic. And they switch back to on-demand for variability during and after the event. Please use these capacity modes to best balance price, cost, and service to your customers. All right, moving on to that topic of caching. The DynamoDB Accelerator, or DAX, is a fully managed, centralized in-memory caching solution for DynamoDB data operations. It deploys as a cluster of instances in your VPC and is then available to clients within the VPC in accordance with an IAM policy. DAX is fully API compatible with DynamoDB, so clients need only initialize a session using the DAX driver instead of the normal DynamoDB SDK session initialization. From there, all of the regular DynamoDB API actions and SDK functions for data operations are the same. DAX is a read-through cache, which means your client does not need to manage populating the cache on the side. You can write through DAX, in which case your writes are synchronously passed through to DynamoDB in order to automatically update the cache with any mutations. Or you can write around DAX and just rely on the next read through DAX to populate the cache. Strongly consistent reads are also passed through DAX, and they do not update the cache. The cached data is expired according to a configurable time to live, and will also apply a least recently used algorithm to evict oldest data from the cache if it fills. We recommend that production use cases always deploy with at least 3 nodes in the DAX cluster, distributed across 3 availability zones in the region. You can scale out up to 10 nodes to serve additional read traffic, and you can scale vertically by node type for higher write activity, larger cache, and greater CPU capability. While DAX in a 3AZ configuration is highly available, we recommend that you build your application workflows to allow for configurable fallback to work directly against DynamoDB should you need to restart or replace your DAX cluster. The benefits for caching can be significant, but an overloaded or unavailable cache can cause many cascading effects within a complex microservice architecture. Plan ahead and build in levers. Follow operational best practices for monitoring and scaling your cache. There's an excellent article in the Amazon Builders Library called Caching Challenges and Strategies, which I highly recommend. Many customers using DAX also employ additional layers of caching throughout their architecture. This could be a small local cache within the compute layer for the application, or within CloudFront, API Gateway, etc. For read-heavy workloads, a properly configured DAX cluster can offer very high cache hit rates, reducing DynamoDB's already low latency to sub-millisecond. It can drastically reduce the number of read units consumed for the DynamoDB table or secondary index, thus lowering your bill, perhaps enough to more than cover the price of the DAX cluster. And finally, it has the effect of smoothing the distribution of traffic across items in your DynamoDB table. The diagram here shows this effect, where items which are running hot do not see notably higher reads against DynamoDB itself. This can be a great operational benefit when your traffic is unexpectedly skewed towards a small subset of your data. It's not recommended to build around this for known hotkeys. You can expect that a single item under 4 kilobytes in size can be read from DynamoDB with eventual consistency up to 6,000 times per second. If you know you'll need to read it 20,000 times per second, DAX might help. But if DAX should be unavailable for any reason and your application falls back to reading directly from DynamoDB, you will see throttling and potential customer impact. For such a known hotkey, you can consider writing the same data under 4 different partition key values and having the application read from one of the 4 randomly. Such a configuration will still benefit from the cache, but will sustain the required traffic even when reading directly from DynamoDB. Disney Plus presented their use of this strategy in a recent reInvent session. So to summarize, for a read-heavy workload which tolerates eventual consistency, you should consider the potential benefits of DAX. Lower latency for a more responsive experience to delight your customers. Smoothing of unanticipated skew in pressure to parts of your dataset. And less read unit consumption in DynamoDB. With high enough cache hit rate, this can easily result in a lower overall AWS bill. Let's talk about backup and restore. DynamoDB provides 2 backup features, one which allows you to snapshot your table and indexes and keep that snapshot indefinitely, and the other, point-in-time recovery, is the feature that I want to cover in this session. Point-in-time recovery keeps 35 days of your table's history available for restore, so you can fully recover your data to any second in the preceding 35 days. We recommend enabling point-in-time recovery for all production tables storing data which is not ephemeral or easily recreated. Point-in-time recovery uses none of your table's throughput and has no impact to your live data operations. Back in my earlier work experience, one of the reasons I kept backups was because I worried about potential for losing multiple disks in an array at the same time, and similar catastrophic infrastructure failures. That's really not the concern in the case of DynamoDB, but there's still a possibility of accidental or malicious table deletion and corruption of the data. This could be as simple as deployment of new code, which inadvertently writes incorrect data to a number of the items in your table for a week before the error is detected. Access to a DynamoDB table is denied by default, and best practice is to allow access according to the principle of least privilege. Fine-grained control to items, even per attribute, is available via your IAM policy, and the various data operations can be allowed or denied based on a number of powerful conditions. Despite all of this, it's possible that a malicious individual could delete a table or modify items. Such a scenario could also be the result of simple human error or a coding error. So how might this impact your application or service? How would you recover? And how long would that take? Here's what the restore might look like in the DynamoDB console. You can see that I must name a table to restore to, and that table must not exist. I get to choose any second in the 35-day window to restore from, and I can choose whether to restore with or without my secondary indexes. If the application is being taken down during the recovery, it might be possible to delete the original table and restore to the same table name, but it's very much more likely that you want to keep the original table and possibly keep operating in a degraded state during the recovery. So you'll choose a new name for the restored table. Something like sense of relief might be appropriate. Now, if you've made the table name configurable in your application, you can roll your operations into the newly restored table. Or you could roll out updated code which builds in a comparison against the restored table items each time you access an item in your live table. Sort of a repair on access procedure. You could also search through the restored table and make a comparison to the live table as a backfill type of approach. Lots of possible paths here, and which is best will be specific to the use case and the recovery scenario. DynamoDB Streams might provide an additional option. Capture your change data with new and old image, store it in S3, and query it using Athena. Something to consider. When you're defining your schema, think about building in attributes which can be used to determine items that need to be rolled back. This might be a timestamp, or it could be a version number for your application software. When considering data protection and disaster recovery, we generally want to define a recovery point objective, how much data am I willing to lose in restoring service, and a recovery time objective, how quickly can I recover. With point-in-time recovery, our PO can be 1 second. Our TO will vary. A table restore takes time, but see our recent announcement about improvements around shorter and more consistent time to complete a restore. As discussed on the prior slide, how you manage your application through a recovery is use case specific. Ideally, we would have a full set of runbooks for various scenarios, but it turns out that business continuity and disaster recovery can be difficult and typically not frequently tested. I would suggest that no matter how prepared you are, having point-in-time recovery enabled will give you options you may be glad to have in your back pocket someday. You should consider the value this adds for the critical business functions you build around DynamoDB. One more thing to note before I move on. When a table with point-in-time recovery is deleted, the point-in-time recovery data is also removed. However, before deletion of such a table, DynamoDB will automatically capture an on-demand backup of the table, as it existed at the time the deletion request was made. This backup data is retained for 35 days and is system-owned. It cannot be removed before this time is elapsed. You might like to make a policy of enforcing point-in-time recovery enablement on all important tables. AWS config may help here, and deny point-in-time recovery disablement attempts via IAM. Monitor CloudTrail for denied requests to delete DynamoDB tables and denied requests to disable point-in-time recovery. When it comes to your critical production tables, paranoia is a very good thing. Moving on to multi-region architecture. Global tables provide a service-managed means to replicate between DynamoDB tables in multiple regions. The table in each region operates like any other DynamoDB table, delivering high availability via storage in 3 availability zones. The normal DynamoDB regional endpoint is used to access the global table regional replica in that region. There's a 4 nines SLA on availability in each region, which extends to 5 nines when you build around a global table configuration. Replication between the regions is eventually consistent and multi-directional. The service takes care of all conflict resolution via a last right wins policy. Many customers use global tables to enable them to fail their applications between regions, allowing them to achieve a higher level of availability. Others are primarily looking to provide a low latency experience for users who may be located in multiple geographic regions. Global tables can also provide a means to meet regulatory requirements. So what does a multi-region architecture backed by a global table look like? There's sometimes a tendency to imagine a scenario where an application stack deployed in US East 1 might want to fall over to a different region of a global table in the event that there is some kind of DynamoDB service impact in US East 1. In fact, the multi-region architectures that we see around global tables involve a complete application or service stack in each region. A failure could result from any part of the stack. A complex system of multiple components is far more likely to see a failure than the DynamoDB endpoint within a region. Here's an example where a customer application is made up of 3 different microservices. They decide to operate in both US West 1 and US East 1 to give lowest latency for users on both coasts, and to allow for continued service should there be impact to one of the microservices in either region. Everything looks good here, but then something goes wrong in microservice C within US West 1. This might be due to a regional problem in one of the AWS services that microservice C is built on, or it could be due to a software problem in a new deployment of microservice C. In any case, our metrics and alarms are telling us that there is a problem with microservice C in US West 1, and microservice A and microservice B are seeing a high error rate when they call microservice C. Based on this, we fail out of US West 1, and we direct our West Coast users to the application stack in US East 1 instead. How do customers manage the flow of traffic for their application? There are many options here. Depending on the data operations required and the business requirements behind the multi-region storage, a customer may choose to run all reads and writes to a single region, an active-passive configuration which gives them the option to scale out the application in a standby region when required. This is the simplest approach for business continuity and disaster recovery. and it is easy to reason around matters of data integrity. Another option we see customers choosing is to make all writes and strongly consistent reads in a single region, but for eventually consistent reads with lowest possible latency, they read from their closest region. This is also easy to reason around in terms of data integrity. To me, the most interesting architecture is an active-active configuration where reads and writes are made in multiple regions. If your data operations are idempotent, such as an append-only table or unconditional updates, this is easy to achieve. Due to the eventual consistency of global table replication between regions, we need to be more careful when using conditional flows. The conditional writes in an optimistic locking pattern, or a multi-item transactional read. We need to be careful to make all write operations behind these activities in a single region. Note that this doesn't necessarily have to be applied at the full table level. It really applies by item. For many business needs, it's possible to pin items to a particular region. Some items might be homed in one region, and others could be homed elsewhere. Perhaps the primary key is named according to a prefix, and IAM can allow or deny write activity in the region based on this. Or you can maintain an attribute in each item which indicates the home region, and your write operations can be conditioned on this being local. You may be able to carefully rehome items. Imagine a user profile for a mobile game. The user might normally be in the US, but perhaps took a flight to Europe to vacation. Their user profile item might be rehomed to follow them. Or you might forcefully rehome items for a particular region if you need to fail out of that region. These are application-level workflows, and it's exciting to consider the possibilities for each particular use case. Most traffic distribution requirements are solved with either manual or automatic changes to domain name records using Route 53. Depending on your use case, you might be able to leverage health checks and use routing policies based on latency or geolocation. If DNS is not reactive enough for your needs due to potential for client caching, you might like to look into Global Accelerator. It can provide latency benefits also. And finally, if you have something like a mobile application, the client could potentially access DynamoDB endpoints directly based on Route 53 policy, and could use federated authentication and fine-grained access control to limit access. In such a configuration, I might recommend architecting with API Gateway serving the client instead, as this allows for rate limiting and caching. Take a look at API Gateway's integrated DynamoDB support. Now, how do we build well and quickly with DynamoDB? NoSQL Workbench is a standalone graphical tool for Windows, Mac, and Linux, available to download from AWS and use at no cost. When building a solution around DynamoDB, the Workbench helps to understand your data and data operations, and allows you to iteratively refine your data model for optimal results. It's composed of three sections: the data modeler, the visualizer, and the operations builder. In the data modeler, you define your schema for DynamoDB. The relevant schema elements are those you will index. And you describe your indexes, base tables, and secondary indexes. Then you can go to the visualizer, you insert some example items, and see how they look from the perspective of each index. While developing your design, you'll likely go back to the data modeler several times to refine that indexing. This is an iterative process made very much easier by NoSQL Workbench. When you think you are satisfied with your design, you can commit your visualization example data to a real DynamoDB table. This then enables you to use the operations builder to easily construct data operations using a graphical interface, test them against DynamoDB, and generate snippets of code that you can copy as a template for your own software development. This approach to building on DynamoDB is very productive, and I highly recommend that builders use it as the basis for your DynamoDB solutions. Let's talk about some of the less obvious ways that I'm seeing the NoSQL Workbench deliver business value. Here we see a screenshot from the visualizer. It's an online bank scenario that I've used to demonstrate DynamoDB transactions. The first thing I want to point out here is the button that allows us to commit our example data and indexes into DynamoDB. This not only enables the operations builder as the next development step, it allows us to very easily create a live environment for testing or for demonstrating the data model we're proposing, using the console, CLI, or SDKs. Next, I want to point out the import and export buttons. These allow us to save out our data model and example data as a simple JSON file. This can be shared so that people can collaborate on the design and suggest changes. It can also be saved as documentation. Years from now, when the development team has changed, this will be easy to import to NoSQL Workbench to understand the model and perhaps to evolve the design to support new features in your application. Finally, notice the Export to PNG button. This allows us to easily snapshot the various views of our example data through our indexes. Again, this is terrific for demonstrations and documentation. When I'm working with AWS development teams and external customers to review DynamoDB designs they'll use, this tool is priceless. Teams use this to develop a proposed model, they share it with others for review, and they save the designs out for future reference. This tool unblocks DynamoDB designs, and it encourages the right strategy for getting great results from DynamoDB. I really cannot recommend it enough. It has changed my life. Okay, so now we have a design. It's time to roll up our sleeves and get coding. DynamoDB offers a free tier, which is great for getting started. 25 gigabytes of storage is a lot and covers many production use cases. 25 read units per second and 25 write units per second may not sound like a lot, but over the course of a month, that's around 130 million data operations. I mentioned that the Workbench Operation Builder will generate sample code for you in Java, JavaScript, or Python. You can also experiment via the console and the CLI, and of course, there are CloudWatch metrics to help you see the impact of your DynamoDB workflows. Take a look in the documentation for a parameter called return consumed capacity. This is an excellent way to validate the efficiency of the choices you've made in your data model and in your application's use of the APIs. AWS offers SDKs for all the popular development languages, and I'm excited to think about what you could build. I'm providing a set of links to resources you may find valuable. The deck will be available for download soon. I also want to highlight a couple of great DynamoDB customer stories shared in other reInvent sessions. Thank you very much for watching. I hope you've enjoyed the session. I'd appreciate your feedback via the session survey. If you're interested in learning more about the range of AWS purpose-built databases, please follow me on Twitter and join me on Twitch, where I host a show called Demos for Devs.